Hello, كيفكم يا شباب؟ I will continue, as I told you in the previous session, to go through midterm 2. Because, of course, before you go through midterm 2, you will have to review all the chapters as we spoke plenty of times previously. Read the questions carefully. Some of the alternative, and this is also another level of difficulty in solving such type of exams. You will have to read the questions very carefully, choose, try to decide if the answer need an extra work from you to prove something, to evaluate something, should be very careful, or the direct, it will be solved directly from the definition. Start to think about this. Okay, for question number 1, he's stating, consider the vector space R3 with the canonical inner product, indicate which statements are true or false. So he's giving you R3 with the canonical inner product. And he's giving you a canonical set, orthogonal set, and also, orthonormal set. And start to remember orthogonal and orthonormal. This is parts from chapter 7. So try to get back with the information from chapter 7. So if E1, E2, E3 is an orthonormal basis of R3, then 1 over root 2 E1 plus E3, 1 over root 2 E1 minus E3, and E2 is an orthogonal basis of R3. So he's just want you to check if it is orthogonal and also a basis. Careful from the word basis. But it is not orthonormal. So let's check that. This is really very simple. All I have to do is to, as you know that E1 is 1, 0, and 0, which is the standard set. E2, which is 0, 1, and 0, and E3, which is 0, 0, and 1. Those are the standard canonical set of vectors. I want to check this set of vectors, which starts with 1 over root 2 E1 plus E3. So actually, the first set is 1 over root 2 of E1 plus E3. So E1 plus E3 will develop 1, 0, and 1. This is for the first set of vectors, or the first of them. The second one is 1 over 2 E1 minus E3. So I will take E1 minus E3. So I believe it's going to be 1, 0, and negative 1. Of course, 1 over 2 is multiplied. And the last one is E2, which is 0, 1, and 0. And this is the set that we want to check if they are orthonormal basis for R3. So the first of them is going to be 1, 0, 1, and so on. Let's check first. Leave the values of 1 root 2 over root 2, and let's see if they are perpendicular to each other or not. Every two of them should be perpendicular in each other or orthogonal. And this is easily can be done by performing inner product. So if I say that, let's say, if I say this is L1, L2, L3, let's check that L1 inner product L2, what's gonna be? So it's 1 times 1, which is gonna be 1. 0 times 0 equal to 0. 1 times negative 1 equal to negative 1. The sum equals 0, so they are orthogonal. Let's check L1 times L3. So I will try to check also. It's going to be 1 times 0, which is 0, plus 0 times 1, which is 0, plus 1 times 0, which is 0. The result is 0. They are orthogonal. Then let's do L2, L3, for example. So it's going to be also 0, 1 times 0, 0 times 1, negative 1 times 0. So it's 0, 0, plus 0, all is 0. So this set is orthogonal. The second thing, to be sure that they are orthogonal, and also it's an orthonormal, because the magnitude of this vector is root 2, and it's multiplied by root 2, so it's actually a unit vector for each one of them. So about the orthonormality part, it's correct, but the basis issue, I will need to check. How to be sure that this set is also normal? Is also normal basis. They should be linearly independent. In order to check that, I will go through 1, 0, 1, 1, 0, and negative 1, and the last one is 0, 1, and 0. Of course, remark that the first vector is divided by root 2, the second is divided by root 2, and the third one is divided by 1. So I will start trying to eliminate these vectors and to see if it is linearly independent or not. And this is how we are going to check if it is a basis. So once more, as I told you, this statement, once we start doing so, we will have an orthogonal basis of R3. Vectors of this basis should be orthogonal. We already checked that they are orthogonal. And they should be linearly independent. They are not linearly independent. So for the first statement, it's not orthonormal basis for, it's an orthonormal, So كلمة not here, the invention here, making it not correct. So this is actually the main issue for this problem. Okay, for number B, for any vectors u, v, and w, we have the inner product of, the triple product, which is an inner times cross product of u, w, inner u cross v is equal to the negative of w cross v of then the inner product. From the definition of this is actually true. So if it is correct from the general properties of the triple multiplication, remember if I have u, this is from the definition of this slide, if I have u alpha 1 e1, alpha 2 e2, alpha 3 e3, and I have v, which is beta 1 e1, and so on, and we have also w, which is gamma 1 e1 and gamma 2 gamma 3, we made this inner product. Of course, if we change the rows due to changing the cross and inner product properties, we will have a negative sign, so it is correct from the definition. For number C, if E1, E2, E3 is an orthogonal basis of R3, just to check these two vectors. All I have to do is to get U1 and UV and writing the law of the cosine angle between these two vectors, and this is also really very simple. So all I have to do is to first getting U and V, U equal to E1, so it's a 2, 1, double 0, minus E3, which is minus 0, 0, and 1. This is the vector that we are talking about. And for V, it's E2 plus 2 over an E3, so it's a direct substitution. I have U and V. The law is really very simple, which states that cosine theta will equal to U inner V divided by the magnitude of U times the magnitude of V, as you can see. So all I have to do is to do the inner product, then dividing on the magnitude. And it's very, very simple. This is 2, 0, negative 1, 0, 1, 2. I will do the dot, the inner product, divided by the magnitude of the first part, which is 4 plus 1, which is 5. And for the second one, which is 5, it's going to be negative 2 over 5. So for this statement number C, it is correct. If I go for D, you have E1, E2, E3. It's an orthonormal basis of R3. Also, U and V are completely defined. They are exactly like the previous one. So U, V, they are exactly like these two vectors. W is 3E1 plus E3. This is the definition of 3E1 plus E3. That's the definition of the third vector. And he's asking you directly about the cross multiplication of U and V. So all I have to do is to do the cross multiplication of the first two vectors. How to do it? This is going to be E1, E2, E3. The first vector, which is 2, 0, negative 1. The second vector, which is 0, 1, and 2. Here we go, this is the second vector. Start from E1, eliminating row and column. So it's gonna be 0, then plus 1, so plus 1, so it's a 1 times E1. For the second, it's gonna be a negative, eliminate row and column, so it's gonna be a 4, so it's gonna be negative 4 E2. For the third one, which is E3, eliminate row and column, so it's gonna be 2, positive 2 E3. Comparing, and this is what I'm telling you about. Once you do so, you should compare your results. So, as you can see, I'm comparing 2E3 to the value. So, it's just only the difference in sign between the given or the value that you have and the given one, which states that this is not correct, so I don't have to complete it. But also, if you complete it for the triple multiplication, U cross V dot W, the result is not going to be correct. So you don't have to complete it. Number E, even though if it was correct, even so, if it was correct, still the whole statement is not going to be correct, so it's done. For number E, he's giving you A and B be vectors in R, just a second, in R3. The vector A plus B and A minus B are orthogonal if and only if the magnitude of A equal magnitude of A. I can do this really very simple by just putting and imagining the components of A and B. So I will start with assuming that A is equal to x1. Let's say that I will consider A has x1, y1, and z1. B have the components which is x2, y2, and z2. Now all I have to do is to get A plus B and the A minus B. So if I want to have A plus a B, so it's going to be x1 plus x2, y1 plus y2, and z1 plus z2. If I'm having A minus B, so it's an A minus B, which is going to be x1 minus x2, y1 minus y2, and z1 minus z2, exactly the same. To be orthogonal, A minus B and A plus B, if you did the inner product of these two vectors, the result should be 0. So once you do this inner multiplication, A minus B, inner A plus B, you will have these two vectors multiplied in each other. So it's an x1 minus x2. You will find here x1 plus x2. Here's y1 minus y2. Here is y1 plus y2. Once you do so, this multiplication should equal to 0 to be orthogonal. If you do so, you will find that you will end up having x1 minus x2 to the power of 2 and plus y1 minus y2 to the power of 2. Okay, it's going to be x1 squared, minus times minus x2 and y1 square minus y2 square and z1 square minus z2 square, and is equal to 0. And this is going to result that x1 square plus y1 square plus z1 square is going to equal to x2 square plus y2 square plus z2 square, which is a condition for orthogonality, which means the magnitude of A plus B equal the magnitude of, the magnitude of A equal to the magnitude of B as indicated from the beginning, because this is the main assumption of an A and B. So it's really very simple. All I have to do, as you can see here, just to make the assumption, to put the two vectors, to make the inner product, and to put the condition for orthogonality, which is equal to 0, just manipulate it a little bit, you will come up with the condition for this problem to be correct. For question number 2, he's asking you to indicate which statements are true or false. And he's giving you f such that from R3 into R4, is a linear transformation, then F is not surjective. This is a breaking for the dimension issue. In order to be surjective, the dimensions should be the same. So the first one is not surjective, this is for sure. Let E and E dash are finite dimension vector spaces. Dimension of E equal dimension E dash. Then any linear transformation is bijective. This is a necessary condition, but it's not the only condition. So it's partially correct for this statement. So once more, if E and E dash are finite dimension spaces, dimensions equal, like R3 to R3, R4 to R4, then any linear this is not a condition for bijection. And I will speak about this just in the coming slide. Bijective, it means this transformation should be two things, should satisfy two things, as you know. Should be surjective and also should be injective in order to be bijective. So this statement will need division. For number G, R3, R4 is a linear transformation. Then moving G function and the 2 over G function on two other vectors should equal to the image of this form. This is going to be correct if the condition of addition and the multiplication in the scalar is combined together is correct. And this is easy to check. 1 plus 2 times negative 1, it's going to be negative 2. So 1 minus 2 plus negative 2 is going to be negative 1. Negative 2, then plus 2 times 3, which is 6. The result is going to be 4. 0 plus negative 2, so it's going to be negative 2, which means that this satisfies the condition for the two sides to be equal to each other. There exists a linear transformation R3 into R3 such that a kernel of F equal to image of F. This is impossible. We already talked about this previously. When you have the kernel of F equal to the image of F, this is going to be satisfied with the even transforms, the even dimension, because of the nullity theory, not with the odd, and we will talk about it. There exists a linear transformation R3 into R4 such that 0, 0, and 1 belongs to the kernel, and image of F is given by this span or this basis of R4. This also will need extra work. So let's start first by R3 is a linear transformation, then F is surjective. As I told you, direct from the definition, there is a mismatch in the dimension. So number A is correct, it's not surjective. For number B, a linear transformation, I'm sorry, this is also more clarification for this statement. I want you to remember what we mean about surjectiveness. Subjective transforms means that the image of the transform should contain, as I told you, should span the entire codomain. And this is for the surjection. It's not going to be easy to have, it's not going to be fulfilled if you have a mismatch in the dimension. I will go for B in just a second. Okay, as I told you, now we will go for B, which, as I told you, the equality in dimension is not sufficient to have a bijection. As I told you previously, bijective transforms means it should be injective and surjective. What we mean about injectiveness, that the kernel of the transform is going to be just only the zero. Surjective, it means the image of the transform should satisfy the whole domain. So injectiveness, which is 1-to-1, the image, the kernel of F should equal to, will be the 0, meaning that only vector mapped is the 0 vector. Surjectivity, which means F surjective, the image of F span the entire view. خلي بالك in the dimension equality, take care that the dimension equality states that F, dimension E, and dimension E dash are equal. If this happens, with it you should have F is either injective or surjective. Now, if it is not surjective or surjective, then it is automatically will be bijective due to the nullity theory, as you can see. Now for question number 2, for number 3, if I have GR3, this property, and this is a direct substitution from the condition of subvector space. Since it is a linear transform, so it satisfies the main properties of a linear transform, which is the addition, closure, and the multiplication of the scalar. They can be combined together in statements like 3 or 4. If you remember, this part is from the slides. So for every alpha and beta, if I have f for u times alpha beta times v, it should be like this. And this is the second statement, which actually we are dealing with. Here is fu, it's already the same, plus an alpha times f of v, and they are equal to each other, so this statement is correct. The transformation, okay. This is what I told you about. If we have R odd dimension, you can't have the kernel of f equal to the image of f, especially for the main domain, because of the nullity theory, which states that dimension of R3 should equal dimension of the kernel because plus the dimension of the image. So these two parts will never be equal to each other, and so number D is not correct. For number E, in order to check for 0, 0, and 1, satisfying the nullity theory, all I have to do is to check the dimensions. So once more, this is from the main slides, and it is about the nullity theory. If I have a linear transform from E into E dash, so I'm making a linear transform, with E finite dimension, then kernel of f, okay, and the dimension of the image, both together should equal to the main domain. So let's write it and start doing this. Dimension of R3, which is equal to 3, and it should equal to the dimension of the kernel, but here you are stating that the kernel contains a vector, so I will consider 1, plus the dimension of the image. The image contains 3 linearly independent vectors. So the left-hand side, actually, left-hand side is 3, with the right-hand side is 1 plus 3, which is 4, and there is a contradiction here between the left-hand side and the right-hand side. So for this part, it's not correct. Now for question number 3, for the third question. Let R3 into R3 be a linear transformation such that for A, B, and C belongs to R, we have the transform. So you are having the function now. I'm giving you the function of f. The function of f, which maps ABC into A minus B minus C, and ABC into A plus B plus C, and 2 of an A. This is the 3 components of this function of a linear transform, where beta and the beta dash be bases for R3. So I'm giving you 2 bases for R3. Okay, G is another function. G is another function, or another linear transform, which maps R3 into R3, and this is the linear transformation matrix. Matrix of the coordinates of this transform from B to B dash. Okay, so the first one, I'm giving you the main function of the transform. The second transform, which is G, I'm giving you the matrix of the coordinate change between the bases of G. Under this condition, write each statement is true and he is giving you number A, B, and C, and D. In this part, or in this question, this is not going to be an easy one. This needs your full attention, go step by step on each point of these points. So I will start with the following. For number A, I want to see the image of 2, 2, 3, and if it equal to 3, 7, and the negative 10. The problem is I'm not giving you the function. If you have the function like f, all I have to do is to substitute by these values in the function, but I don't have it. I have instead the matrix of the coordinate change. This is stated here. We will have to go through step by step, get the corresponding coordinates to the vector 2, 2, 3. So now I will need to get the corresponding coordinates of 2, 2, 3 based on the basis of G, which is given by 0, 1, and 0, 2, 0, 0, 0, negative 1, because you are moving from R3 into R3. So I will start with this basis. And this is very, very simple. All I have to do is to take our vector, which is 2, 2, 3, and use the basis, the given basis of B, which is 0, 1, 0, 2, 0, 0, 0, 0, negative 1, using the coordinates A, B, C, alpha 1, alpha 2, alpha 0, x, y, z, you will end up having a system of equation. We did that plenty of times. You will find that done in your main slides or in your main lectures plenty of times. So now I will have to get the coordinates, which is x, y, and z. All I have to do is to solve this system of equations. So it's going to be 2 equal to x times 0, y times 2 plus z times 0. This is for the first component. And for the second component, it's going to be an x and 0 in a y and 0 in a z. This is for the second component. For the third one, it's going to be also 0 times x, 0 times y, and a negative z. This is the third component. You will end up having these three equations. So equating the first coordinate by the first coordinate, you will have 2y equal to 2. And for the second component, by the second component, you will have x equal to 2. For the third component, with the third component, you will have z equal to negative 3. So actually the values are x equal to, y equal 1, z equal to negative 3. These are the coordinates of this set. So if I use these coordinates, with the basis of beta, I will have my vector. Now to the point. I will use the matrix of the coordinate change between the bases. Now I have 2, 1, negative 3, which is the combination of the vector with respect to beta. So all I have to do is to multiply this vector, or this coordinate vector, with the matrix that's given to us connecting this transform, and we will have the corresponding coordinates. The corresponding coordinates. But with respect to B dash, so after the movement. So actually, taking these values, these results, which is negative 5, negative 3, and 7, and multiply it in B dash, so it's going to be a negative over 5 times, okay, the first vector, 0, 0, and 2, then plus multiply, for the second coordinate, it's going to be a negative, so we multiply, as I told you, negative 5 by the first vector, okay, and negative 3 by the second value, negative 3 times the vector that we have. We are doing a multiplication. These are the coordinates, so it's a negative 5 times the first, then, plus a negative of a 3 times the second one, which is negative 1, 0, and negative 1, 0, and 0, and the last one, which is 7, and you will multiply it by the 0, 1, and 0. So the result will be the following. Negative 5 times 2, it will develop negative over 10. Negative 3 times negative 1, so the first component is 3. Then 7 times 1 is going to be 7. So actually, the vector or the image is going to be as 3, 7, minus 10. And this is exactly what's given, 3, 7, minus 10. So once you have these values, and I will multiply it by the B dash, these values, I will multiply it by B dash, as you see. Then I will compare it with the result, so it's correct. So now you saw, okay, once more, now you saw, I don't have the function that will give me the image of 2, 2, 3. Instead, I've used the matrix of this linear transform. And so all I had to do is to get the corresponding coordinates in the codomain. So all I have to do is to get 2, 2, 3. I'm seeking the coordinates, but in the main domain, which is x, y, and z. I will solve this system of equations simply getting y, x, and z, or x, y, and z, which are the coordinates in the main domain, multiplying these coordinates by the matrix of coordinate change, here, we will get the corresponding coordinates in the codomain, which are -5, -3, and 7, multiplying these coordinates by these vectors, which is the basis of the codomain, will develop your matrix, which is simply, as you can see, -5 times 2, which is going to have -9, -10, -3 times -1, which is going to develop the 3, and 7 multiplied by the last vector in this basis, which is going to develop the 7 in the middle, so we are in a very good shape. Here once more, this is the comparison. Now, for number B, I'm talking not about G like the previous problem, but now I'm talking about F, which is a little bit simpler, because I'm giving you actually the function given in your problem, and I'm asking that F, it will map the canonical basis of R3 into B dash. Make this linear transform. So let's get the matrix of the coordinate change in F from B into B dash. Now let us find the image of the canonical basis of R3 using an F linear transform. This is very, very simple. All I have to do is to get the image of the canonical basis, which is 1, 0, 0, 0, 1, 0, 0, 0, 1. So I will insert, here's A minus B minus C. For the first vector, which is going to be A, 1, minus 0 and 0, so the element is going to be 1. For the second component, same way like, it's going to be A plus 2 zeros, so it's going to be 1. For the last component, it's going to be 2 times A, so it's going to be 2. So this is for the first vector. I'm taking a component by component, substituting the values of the vector into our function, and you will have the corresponding components, which is in the codomain. Same way like for 0, 1, 0, in a similar manner, this is going to be a 0, this is going to be a negative of a 1, this is going to be a 0, so the first element is -1. I will take 0, 1, and 0 and do the substitution A, B plus C. So it's a 0 plus 1 plus 0, so it's going to be positive 1. Then I will go for 2A, which is 2 times 0, which is going to be 0. Same way like for E3, it's going to be -1, 1, and 0. These are the 3 vectors in the image or in the codomain for the canonical basis. Now let's find the coordinate of these vectors considering the B dash or the other basis of R3. Our vectors are 1, 1, and 2. I'm getting now the matrix of the coordinate change from B into B dash. So there's the first vector, which is going to be a linear combination, but with respect to B dash. So it's an A, B, and C, X, Y, and Z. I don't want to use X, Y, and Z in order not to confuse you, so I've replaced them with A, B, and C. So it's an A, B, and C. And these vectors are the vectors in B dash. So this is 0, 0, and T, -1, 0, 0, 0, 1, and 0, which will develop A times 0, B times -1, C times 0. So for the first component, B minus 1 equal 1, which means B equal -1. And also in all of them, I'm equating the components on the right-hand side with the corresponding components on the left-hand side, and so I can be able to evaluate the values of A, B, and C, which are the coordinates, exactly like what we did. Now we can get to the matrix of the coordinate change, which is 1, -1, and 1 for the first column, 0, 1, and 1 for the second one, and 0, 1, and 1 for the third one. Now we come to the comparison between this matrix and the given one. The first column is correct, but the second column, it's missing a minus sign, and exactly the same for the third one, so number C, it is not correct. See how delicate is this analysis. I should have a good understanding about the matrix of coordinate change, how to get these coordinates together, and you will never have this unless you solve at least the problems in the main slides plus the problems that we are solving at the time being. Okay, in a similar manner, for number C, is asking you about the kernel, a kernel of an f, which is a simple task because the kernel of f will depend on the following. I will get first the image, put it into 0, getting the conditions, then resubstituting in ABC, I will get the value. So, get the kernel of f. All I have to do, this is ABC, belongs to R cubed, such that the A, B, and C, the image, equal to zeros, which means that A minus B minus C, A plus B plus C, and 2A should equal to 0. All of this should equal to 0. So I will have three equations, 2A equal to 0, A minus B minus C equal to 0, A plus B plus C equal to 0, and this is really very simple. So this is what I have for equating the third components all together, A equal to 0. This is from the second and from the first and second components, which indicates that B equal to negative C, both of them, they are identical equations. So C should equal to negative V. I will take this information, A equal to 0, C equal to negative V, and substitute in ABC. So ABC, I will take A, put 0, replace B by negative C or vice versa. So this is the shape of the vector that we have, which is 0, 1, and the negative 1, which is exactly like the one is given, 0, C, and negative C. So we are in a perfect shape. So it's correct. Now, for number D, with the same question, he wants you to check if 1, 1, and 0 belongs to the kernel of G. The problem is, with this problem, is you don't have the function. So how to do this? I will do it this way. We already know that the kernel of G is that for V, such G of V equal to 0. So once V equal